we'll go ahead with trusses. We'll model this in Scia Engineer, then cross-check our results with these hand calculation results. Then let's dive in. We'll choose our members which we've created. This is a four-sided structure or parallelogram. Putting a support your pin fits the pin support with a hinge support, with a sliding support here. From our analysis or observation, this structure won't be stable. It will surely fall under this self weight or deflect to the right or to the left. Putting a cross brace, we've introduced a cross brace. No, this is analogous to what we see in portal frames or in warehouse design. You see those braces assist in lateral deformations. So this is an essence of a truss. For this, if loaded under gravity load, for this member to fail or for this member to deflect or deform, this will have to fail or will have to buckle. So this gives it rigidity. So, or each member will have to follow such buckling or deformation mode for this to fail. So this is the power or the efficiency of trusses. Escape. We'll select this. I'll change it. Change it to a diagonal. Go ahead, add supports. First of all, add our hinge support. A hinge support is restrained against horizontal and vertical movement, but it's free to rotate. Also other sliding support, which is then restrained against the vertical movement. So in doing this, we'll see we'll have three reactions. So our members are stable. So this is stable structure. This can verify such formula on this, where N stands for the joints, M stands for the members, and R for the reactions. So this is usually M plus R is greater than or equals to 2n. So that will give you if your structure is stable or unstable. So you need to go back to cross check or reread some of these assumptions made on the analysis of trusses. So we have external stability slash instability and internal stability slash instability. So that you could cross check. We jump back to the modeling. So we head back to loads. No, not this one. To loads case. We'll delete this. Let's just have this. This is a simple analysis. You're not designing, so don't really need much. Let's head over to this. So remember, trusses are loaded on its nodes, or it is assumed to be loaded on its nodes. So we'll load 10 Newton, 10 Newton. We head on dead load. We'll define load of 10 kilonewton. 10 Newton, 10 kilonewton. This is arbitrary, so we'll still get the same answers but in different units. But let's assume it's 10 kilonewton. No need to going back to changing this. So assuming this is 10 kilonewton in the global coordinate system, we'll add this. We'll add this on Z since it's a gravity load pattern, then words. We'll add this here and we'll add this here. We'll head over back to the node. I'll add it on the positive S direction. Positive S direction. For the attribute equilibrium, we used to say that the force will have to be equal to what the mass times is acceleration, that's F is equal to ma. So for that to be, there won't be any acceleration for it to be in equilibrium. So in observing this, for this not to, there should be a reaction opposing this. For this, I have to push this member towards the right hand side. There should be an opposing members, so there won't be any acceleration towards the side. So forward and so. We'll then do the analysis and we'll cross check. Go over to calculation. And recalculate. So we'll go We check the external reactions. So getting back to this, we could see we have reactions in the vertical and horizontal. Due to this summation of all the forces acting in the x direction horizontally, we only have just one plus the unknown, so they will give you -10 acting in the opposite direction. Summation of the vertical forces acting we have two vertical forces acting downwards, also two counteracting it, so they will be positive and this will be negative, and we have 0, so they cancel out themselves. Head over for us to find. This is a simple calculation. Take moment against A, check it, then you get this, then you have D, then your D will determine, and the rest. So your internal forces, method of joints, if you are using method of joints or method of sections. So this we'll check with our software. So the calculation is done. Let's head over to the result tab. Let's head to the results. Let's check the reactions first. So reactions. Sorry. We'll consider just the dead load. That is self weight. And this self weight wasn't considered. All that was considered are just the loads acting on this, the gravity and the laterals acting on this. So head over. Dead load, global houses, RS, ROI. Let's go with RS first. Refresh. As you can see, we only have acting in the negative direction to cancel out this, which you can check -10. -10. -10. There's no reaction previously. I will check that and I'll get 20. Head over 20. So checking our reactions, we'll see that our program is right in its calculation. Let's check the displacement of the nodes. Well, this you could suggest how it will move. in the S direction. Very, very, very minimal. Then in the Z direction, 0.03 millimeters. That is very, very almost negligible. So that's by the way. Then there's another thing we'll go over to check those members and acting intentions, because members in trusses are axially loaded, and then they'll have axial effects or actions. Over to the internal forces. With the members, we'll look, those are in compression and those are in tension. So this in red are in compression. This is basically easy to know. This is what I meant to get. Compression, and tension. But this load is pushing this node and it's trying to take it to this way. This will try to restrain it in this sense. In its sense, we will experience tensile forces. This is trying to keep it because it's trying to restrain it against that it experiences compression. This definitely experiences compression, but this node is moving. This practically do not, but they are working in tandem. That is a closed member, so it has its own function, but experiencing neither compression nor tension. Then we'll see so we're checking up on our members. What do we have? In joint A, AD 0, which we've seen BC, which will be 0.2, AB minus 10, AB minus 10, and in calculation on in the assumptions, negative is taken as compression while positive is taken as tension, which is which you could see in the sense that in compression members are shortening, so it's minus, taking it off. So minus 10 compression, positive tension, minus 20 compression. So there goes it. Our first truss modeled. So now let's take a look at our 3D stress. We'll end up activating, let's activate volumes. Considering the dead load or stress on the deformed shape. So you can see from observation, this is in tension, it's compression, this is in compression, this has been increased. Looking at it is tension. Looking at this, since it's been decreased, looking at it decreased from this, then looking at this, not much has been changed. So these members are in compression, where this is in tension. By looking at the values, you will see this is experiencing more compressive stress as compared to this. So about this color, about this somewhere in between here. Why this is red, so it's also expensive tensile force. That concludes this part of the tutorial. Thank you, and kindly subscribe for more of this.